So in this video, we get to start something pretty great in statistics, is we get to create a confidence interval. Now, a confidence interval has a lot of great applications because so far what we've done in previous videos is we looked at probabilities of a person or a group being within a certain interval. This is a problem where we get to create our own interval, and it's going to be creating an interval from a sample, and then we can kind of say, like, okay, so we've got this sample of people, we have an average of this sample of people. Can we actually hypothesize a parameter? And a parameter is something that's really great, because a parameter is actually the average of the entire population. And I mean, we just don't usually have time to ask every single person their opinion. So what we like to do is we like to use the power of inferential statistics to say, okay, I have a representative sample of the entire population, and I'm going to take their average and determine the parameter, which is like the average of the entire group, which is pretty exciting because then you don't need to ask everybody. But there's going to be some margin of confidence. Like, we're not going to be able to say with 100% accuracy, and nor should we, that the small sample represents the whole with 100% accuracy. But this is the power of inferential statistics, is to take a representative population and to say, okay, we've got your information. Now what can we say about everybody? It's really great. So let's get down some of the basics here in the vocabulary and in the basic knowledge here of inferential statistics and what all this stuff means. Now, inferential statistics. There we go. Inferential statistics is the sample data. So we're going to take a small representative sample. The sample data will help us to make an estimate of a population parameter. And the population parameter we're going to be focusing on is the average of the population, AVERAGE. So X bar is going to be the average of our small group, and we're going to try to estimate the unknown average of the entire population. So these are two different symbols, but they both stand for average, but they mean different things, because this is the average of our small group, and this would be the average of the entire population that we can't survey. It's not feasibly possible. There's very few times where we actually try to count every single person, and this inferential statistics is going to be the best key or tool. Now, a confidence interval. This is an interval of numbers providing a range of reasonable values where we expect the parameter to fall. An interval of numbers providing a range of reasonable values where we expect the parameter to fall. Now, you've probably been in a situation where you had to get your car repaired, but the mechanic kind of didn't want to tell you that what the exact price was, probably due to the fluctuation of labor costs and the price of parts. So sometimes they give you this confidence interval. Well, they will say like, oh yeah, this repair is going to be anywhere between $150 to $200. Well, that means is that he's expecting the average to be around $175, give or take $25. So this is him giving you his parameter, which is, you know, the average of what he expects the entire population of this repair to cost, give or take the standard deviation. Now, obviously, he's guessing that parameter based on his sample data, which is basically him or her looking at the price of what it would cost to repair that vehicle. And then he's or she is giving that kind of like upper and lower bound there. Now, to find this confidence interval, we are going to take our average of our sample group. So again, in the example of the car repair, maybe the average is $175, and that's easily findable if you just, you know, put it all on a spreadsheet and take the average of all the repairs, right? But then what you need to do is you need to create that error that's higher and lower than the $175 that would give you that spacing that the possible true average, also known as mu, would exist. So what we call this is we call this the EBM. EBM. All right, so let's explain how we find our confidence interval with these two definitions, or these two symbols here. We can find the confidence interval, and it's found by taking our sample average, also known as X bar, and this is my words here, the give or take as a margin of error and we call that the EBM. So again, the mechanic would say, okay, well, my average repair is 175, give or take 25, so I'm going to tell my customer is 150 to 200. That average is something that he or she can easily figure out, but the EBM stands for, and we're going to show you how to do this, you know, get these values here. The EBM stands for the error bound for a population mean. So the E, the B, and the M is the error bound for the mean. Okay, that's what the EBM stands for. Now, we're going to give you a theoretical answer to this problem here. Let's just say that the point estimate for the test is 75 and the error bound for the population mean, EBM, is 5. Then this is what you have. You have your point estimate, which is another way of saying your sample average. And then you have your EBM, which is 5. So that's literally given to you right there in the problem. So you're going to then create something called an interval notation. So you're going to have your X bar, which is your average, minus the EBM, which is going to give you your lower number, and your X bar then adds your EBM, which is your higher number. So let's say that this is a much easier car repair, where the mechanic says, okay, looks like your repair is going to be $75, give or take $5. So what we're going to do is we're going to go 75 minus 5 to give me my lower bound, And then we're going to go 75 plus 5 to give me my upper bound. And 75 minus 5 is 70. 75 plus 5 is 80. We're going to separate this with a comma and put parentheses around this. Now, if you've taken other math classes, you might think that this is an x and a y coordinate on a plane. But in this class, in statistics, this is something called an interval. And the interval notation means that we're going to go from 70 and 80 exclusively, which means we're not going to include the 70 or an 80. So between 70 and 80 is going to be the actual true average price of your car repair. Now, I don't know about you, but I don't think I've ever paid for a car repair in, 10s and 20s. There's always been some kind of decimal due to tax or some kind of add-on that always makes the bill a little weird, like $76.27. So I would say it's still legitimate to not have hard parentheses around these, because if you had hard parentheses, that means we probably could include the exact $70 and the exact $80. But that's why these are parentheses, because in statistics we are never going to be 100% sure of anything, so we put our soft parentheses on there to say, well, we're not actually going to cover exactly 70 and exactly 80. We're just going to say between the two of them. Now, we're going to get into some actual chart reading, and to finish this video here, we're going to really dive deep into the Z chart, so you're going to want to have that in front of you. And I've got mine right here, and we're going to hang around the positive values side, but you can use the negative values side too as well. And once we're done kind of finding things on the chart, we're going to get to some numbers that we're going to constantly use for these to give us the best results with technology. So we're going to deal with the error. The error of a problem is denoted by the Greek letter alpha. And the Greek letter alpha looks like this. Okay? It's a little alpha. Now, sometimes people create this thing that looks like that, and that looks like a fish, like ichthys. But we actually are going to create an alpha. Again, it's kind of a downstroke, and then you kind of double it back, so it looks like the letter A. That is alpha, and I am going to write that underneath, because we're going to be calling this alpha. And it's a lowercase alpha, so that also makes things a little trickier sometimes. But alpha is the Greek letter for error. And the resulting confidence level is always 1 minus your alpha. Okay, so let's just take a look at this quick example underneath this blank. If the confidence level is 80%, then your alpha is 20%. Okay? So subtracting the alpha from 100%, or 1, will give you the complement of your confidence level. So if you say I'm 99% confident, then you have a 1% error. If you are 90% confident, then you have a 10% error. Therefore, alpha and the confidence level are complements. Okay? So now, I hate to tell you this, but an 80% confidence level is wickedly low. In fact, we are going to have 3 staples that we're going to use in this chart. And I did create an extra column here of the lookup numbers that may not be on your chart, so just try to squeeze it in there. So the big 3 in statistics are 90% confidence, 95% confidence, and 99% confidence. These are the big 3. Things that are lower than 90% confidence are usually seen as less valid, because the further down you go, the less sure you are about the actual results. So just learning what we just using what we just learned, if we have a 90% confidence level, then the alpha is 10%. Okay, so that's just these two add up to make 100%. So if I'm 90% confident, I have a 10% error. And if I'm 95% confident, then I have a 5% error. And if I'm 99% confident, I have a 1% error. So when that mechanic gives you the statistics and says your car repair is going to be $75, give or take $5, what confidence level are they speaking to? I mean, you don't actually know that. They may not actually just bore you with the details of what regression and what kind of z-score or t-score analysis they're doing. But let's get back to the problem at hand. What we need to do is we need to take our error and we need to divide it by 2. Now you might be wondering, like, why do I do that? Well, remember that we have to have a give or a take, or a low number and a high number. So we're not going to be off by one possible high side. We can be off by the high and low. And that means we have to split our error into a top error and a bottom error. So this is going to be 5%. Dividing this by 2 is pretty straightforward. It gets a little bit trickier with some of these numbers here, because this is going to be 2.5%, and then this is going to be 0.5%. Because when the mechanic gives you their estimate, let's say it was a big repair, and the person said, okay, I think the repair is going to be $500, give or take 100. Now you can see that the worst diagnosis here normally would be 600, and the best diagnosis here would be 400. And of course, you're going to have, things outside of normality that will be higher than 600 and lower than 400, but according to a standard deviation, those are going to be more rare. So now what we have to do, because what we want to do is we want to find this. This is going to be our goal here, is to find our z alpha divided by 2. Okay, that's our goal. We want to find this, and we want to find that because that is going to give us something we need for our EBM. So we need to go and look up 5% on the z-chart, and we're not going to look up 5% on the columns or the rows. We're going to look at it in the center of the chart, because this is our percentile we need to find. So to look up 5%, first of all, let's just think 5% is 0.05, right? 0.05, that's 5%. But let's add 3 zeros, because I think my chart has 5 digits in it. So by adding a third 0, this is something we can try to look up in the center of the chart. Now, since we are also looking at the high end of error, it might be easier for us to look up this, the 95% with 3 zeros. Now, what this means is that at these 2 places, I can find a z-score that is going to be what I will use for my EBM. I need this z alpha divided by 2. So let's diagnose what we've done so far, and then we'll dive in and get the answer. We have a 90% confidence level. We have a 10% error. Our alpha is divided by 2 because we have a high and a low. And then we're going to look up these on the chart. Okay, so now we're going to look up, I'm going to go and look up the 9500. 9500. Okay, so here's what I found. I found a 9503 and a 94950. It looks like 1.601234. Looks like 1.64 is just a little bit closer than this one here. This one seems to be 3 off. This one seems to be 5 off. So this is going to be 1.64. That seems to be my value here. I'm going to go to my chart and I'm going to use 1.64. All right, so now I found my z of alpha divided by 2, and I'm going to kind of do this for the other ones too. I'm going to then get all of these listed, and then I'll tell you what to use if we had a more accurate chart, if we actually could go further with decimals. So then let's look up 95%. So a 95% confidence means I have a 5% error, or a give or take of 2.5% on either side. Now 2.5% is 0.025, and I'm going to add two more numbers, so this is the number I can look up on the chart. Or I could look up the complement of that, which is 97500. So I'm going to go to my chart. I'm going to look up 97500. 97500. 97500. Now this one is great because it's right here on the chart. No guessing between two numbers. So this is 1.90123456. 0.9750. And this one is so important, I would feel very confident if you wanted to, and I said this is a no-no, but I would feel very confident if you wanted to circle or highlight that, because that is one that we're going to be looking up quite a bit. The 95% two-tail, or alpha divided by 2 value, is incredibly important. So we're now going to use that value of 1.96. Okay, that's the one we found on the chart. Now, I'd like you to try to write your lookup numbers here. You try to write your lookup numbers, because this is going to be 0.05, which is 0.005, and we add two more zeros because my Z-chart has 5 numbers, and the complement of that would be 99500. Okay, 99500. I'm going to look that up. 995, here's 99560. Trying to find 99500. So let's look up here. I got 99506. So that was close. That was 6 away. And this is further away. So this is not great. This is 8 away. So again, this is a number that we look up so often. I think we are safe to say that we can highlight this too. And can we go back and look up the 1.64? Sure. 1.601234. Here we go. Here we go. There it is. So these are 6 that you can permanently deface your chart. Just deface your chart, because these 3 numbers are going to be 3 that you look up quite a bit. And this then would be the 2.56. Now what you might be wondering is, like, hey, how come we didn't look up the 0.00500? Well, the reason why we didn't is that I find that students find it a little bit more difficult, and what you'd get is the same thing but a negative value. So if I look up negative 2.56, so if I go to the 2.58, and so here I am at 2.58, this number is actually the one we would choose because it's closer to the 0.0500. See how this is only 6 away and this is 8 away. So don't write on your chart here, but I'm focusing on these two numbers. See, this is a little bit more challenging to find, but this number, that the 0.00494, this is actually closer to my 0.00500, since it's only 6 away. So I just find it's easier for students to focus on the positive numbers, and we use the positive number anyway. So let us play with a non-standard confidence level that's sometimes used. It's 92%. It's not as common as these 3. I mean, the gold standard is 95%. This is the one that by far is used the most. But 92% is used, and so why don't you try filling out your alpha divided by 2, the lookup numbers on the chart, and then try to get your z-score. Okay, so hopefully you've tried that. This would be 8%, this would be 4%, and this would be, making it 4%, and then adding 3 zeros. Take the complement of that, so the complement of this is going to be 96. And now I'm going to look up 96 on the chart. So 96. And it looks like I'm 80 away right here. Okay, now this is better, isn't it? Because even though it's under my 96,000, basically, it's only, it's only like 6 away from 96,000, or 0.96000. So this is 1.71234. Now don't deface your chart. Don't highlight this on your chart. This is one of those that you're going to want to not mark your chart up, because this one doesn't come up as much. So this is 1.75. Now what I'd like to do is I'd like to give you a couple more decimals. So these are the ones we're going to use for the semester. So add a 49 to this, because my Z chart only goes to 2 decimals. So I'm adding these 2 decimals here because this will give you a more accurate answer. Now, don't add any more decimals here because 1.96 would just be zeros. This would be 0.258. That should have been an 8, but let me erase this and give you something a little bit more accurate than 0.258. 25758. And this is going to be 1.7507. So please use these Z alpha divided by 2 numbers. And these are really the 4 that you're probably going to see on homework, but if you see other ones, use your Z chart to convert. Now in the next video, we are going to get to use the formula, because the formula for our EBM is our Z alpha divided by 2, so these values in the last column, times the standard deviation divided by the square root of the sample size. Oh, check it out. Look, it's our good friend from the central limit theorem. It's the standard error of the mean. All right, this is awesome. And so what we're going to do is we're going to have our sample statistic right here, our point estimate, our average of our sample, belong to a normal distribution with our average, which is the same thing as the average of our sample, and our standard deviation divided by the square root of n is going to be our standard deviation here. So this is awesome. You've been practicing for this moment, getting ready. I appreciate you sitting through all the theory here, because now what we get to do is we get to dig into the problems and get our answers, which is going to be great because we're going to use our T-score or Z-scores, and we're going to use our calculator. All right, getting ready for video number 2 in confidence interval training.